Here's an application of some of the concepts in kinematics and dynamics that we are dealing with. This application arises in many, many different areas in the real world. For example, it arises in the description of this device that we are using right now, the light board. And it arises in fiber optic communication. It's related to something we will discover as TIR. TIR means total internal reflection. We're going to look at the critical angle and its role in TIR, and it's really a mixture of dynamics and kinematics of optics. Or you can think of it the other way around, kinematics and dynamics, but the two are kind of interlinked. So let's look at a situation where we have an interface between a slow material, glass, and a fast material, air. Clearly, the index of refraction of air is very close to unity. The speed of light in air is very close to vacuum speed, and it's slower in glass. Now we know that when an incident wave comes in, and the wavefront, of course, will be like that, and that's the normal to the wavefront, it hits the boundary and gets refracted. So the refracted wavefront will be like this, and because this is faster, we move away from the normal. The refracted ray is bent away from the perpendicular. So let's look and see what happens. We have now theta incident and theta transmitted, and as we change theta I from vertical, and if it's vertical, everything will be going up and down, but then as we open up the angle, the refracted ray starts to swing away from the perpendicular. And as it swings away further and further to say something like that, this particular direction will swing up to theta t will actually approach pi over 2 or 90 degrees. As we open up theta I, theta t is approaching 90 degrees. Therefore, intuitively, you can expect, and you can show this very formally, which we will do later, there's no vertical downward energy transfer, and this is in the positive x direction pointing down. So the first step is to actually compute for which value of theta I is theta t equal to 90 degrees. And that is obtained, of course, using our relationship of Snell's law. We're going to continue with our calculation of the critical angle. It occurs when we have slow over fast, incident transmitted. When there is no refraction that's going down, in other words, the angle theta t is pi over 2, we can calculate at which angle that occurs if we know the indices of refraction. We're assuming that we are working in glass. So glass is non-magnetic, and we use mu0 for the mu. Snell's law we know from here, from optical kinematics. So when theta t is 90 degrees, the sine is 1. What is the critical angle? Well, n1 sine theta c, which is the critical angle, is equal to n2 because that's unity. So simple algebraic equation allows us to solve for sine of theta c, n2 over n1, and theta c. And for glass, theta c is about 41 degrees when the interface is glass to air. And that's one of the main considerations we will look at. The other is glass to glass to glass, and that's optical fiber, or just glass. We'll also look at that. The most interesting point is what happens if the incident angle is greater than the critical angle. In other words, we go beyond, in the case of glass to air, 41 degrees. That's a subject of analysis of what does the sine of an angle mean. Let's continue on with our analysis of the critical angle, and this is key. We know that at critical angle, n1 over n2 sine theta I is equal to 1, which is sine theta t. And of course, as we saw in the previous panel, theta t is 90 degrees. Now, what happens when theta I gets bigger than the critical angle? This quantity here gets bigger than 1, because if I take an angle bigger than the critical, sine is getting bigger. And since at critical it's equal, this whole thing is equal to 1, when we go beyond critical, this number, sine theta I, gets bigger than sine theta critical, so we're bigger than 1. So now we have a peculiar situation where sine theta t, which was 1 at critical, now gets bigger than 1. Let's compute the cosine of theta t. Well, we know that cosine squared plus sine squared is equal to 1. So we rearrange that, and we get plus or minus the square root of 1 minus sine squared theta t. But sine theta t is bigger than 1. That means the inside of this square root is negative. And so this is a purely imaginary number. We have the choice of two roots. Two questions remain. One is, which root do we pick, plus or minus, or which sign? In order to do that, we have to go to dynamics. That's the first question. Second question is, what does this mean? Sine of theta t is greater than 1. When the sine of theta t is greater than 1, theta t becomes a complex number. It means a complex angle. And that complex angle has a growing part that's related to the complex, the imaginary part of theta t. So that has some difficulty in interpretation. However, we'll get the interpretation indirectly when we compute the cosine of theta t and look at dynamics.